Hello everyone, my name is Yong. I'm a third-year PhD student from Tianjin University, and my supervisor is Professor Baoming. It's my great honor to have this opportunity to share some of our research related to the theory of critical distances. The subject of my report is the equivalence of TCD and FFM for fatigue limit prediction of notched specimens, as well as the stress ratio dependence of the input material parameters. My report contains two parts. The first part is some discussions about TCD and FFM for fatigue limit prediction of notched specimens. In this part, we mainly derived the analytical expressions for fatigue limit prediction based on TCD and FFM, and discuss the difference between them. The second part is about the stress ratio dependence of the used material parameters, that is the fatigue limit and the fatigue crack growth threshold. In this part, a new stress ratio correction model for these two parameters is proposed and compared with some existing models. Now, let's start with the first content. I believe most people attending the meeting are familiar with the TCD. In our work, we only considered the point method and the line method. We should point out that the critical distance are material constants in TCD, depending on the fatigue limit and the fatigue crack growth threshold of the considered material. Another theory used to predict the fatigue limit is the finite fracture mechanics. We considered two coupled FFM, which is denoted as PMFFM and LMFFM. The coupled FFM contains two criterions, the energy criterion and the stress criterion. Let's take the PMFFM as an example to illustrate how the coupled FFM works. In most cases, the parameter K increases with the increase of crack length. The energy criterion requires the effective stress intensity factor range larger than the threshold delta kth. This means that there is a minimum distance satisfying the energy criterion. Different with the trend of parameter K, the stress decreases as it moves away from the notch tip. The stress criterion requires the stress range larger than the fatigue limit. Therefore, there is a maximum distance satisfying the stress criterion. Fatigue failure is assumed to occur when the maximum distance determined by the stress criterion is larger than the minimum distance determined by the energy criterion. The fatigue limit corresponding to the condition when the minimum distance is equal to the maximum distance. Different with TCD, the critical distance in the coupled FFM is a structural parameter. It takes both the geometry and material properties into consideration. To obtain the analytical expressions based on TCD and FFM, we should first know the expressions of the stress field. We compared some existing expressions in the literature and found that the expression proposed by Xu is the most accurate. The parameters in this equation are related to stress concentration factor, which can be easily obtained from the handbooks. And this figure shows the consistency of the stress field calculated by this equation and that calculated by FEM. This figure shows the stress intensity factor used in the FFM. From this figure, we can see when the crack is short, the stress intensity factor obtained by this equation agrees well with the FEM results in the reference. This is enough for the FFM because the critical distance is usually small. Based on the stress expression and TCD, we can obtain the analytical expression for the fatigue limit prediction. The parameters in this equation can be easily obtained when the stress concentration factor is known. For an infinite width plate, it tends to be 0. The analytical expression based on the line method can be simplified as this equation. This equation can be used to describe the effect of hole size on fatigue limit. When the radius is large, this term tends to be 0, and we can obtain a familiar equation. As the radius decreases, we should obtain a larger fatigue limit, which can be successfully described by the derived expression. Next, we'd like to derive the analytical expression based on FFM. However, due to the complex form, it is not easy to achieve. We notice that the stress criterion in the FFM is the same as that in the TCD. The difference is the way how the critical distance is determined. If we can obtain the critical distance in the FFM, then we can use the derived expression based on TCD to calculate the fatigue limit. Just replace the critical distance in TCD with the critical distance in the FFM. To obtain the relationship between the two different critical distance as well as the structural parameters, numeral calculations was carried out by using MATLAB. The goal is to obtain the critical distance and the different notches. By calculation, we obtained this figure for PM-FFM and LM-FFM. Through fitting, we can get the expression of the critical distance in the FFM. Then we validate our analytical expression by the experimental data. Table 1 shows the material properties, and Table 2 shows the dimensions of the considered geometry. The result is shown in these figures. The x-coordinate is the predicted fatigue limit, and the y-coordinate is the experimental fatigue limit. Among the four methods, the PM is the most conservative, and the PM-FFM underestimates the fatigue limit. From the perspective of structural safety, PM is more suitable for predicting the fatigue limit due to its conservatism. And from the perspective of statistical analysis, LM and LM-FM are more accurate due to its lower error. We further studied the difference between LM and LM-FFM. This figure shows the difference between the predicted fatigue limit by these two methods as a function of radius. Totally speaking, the difference is small, and these two methods are almost equivalent. The difference increases firstly, and then decreases as the radius increases. To explain this trend, we can see the right figure. This figure shows the ratio of the critical distances as a function of radius. When the radius tends to be 0, these two different critical distances tend to be equal. Therefore, the difference is small. The fatigue limit difference is small when the radius is small. As the radius increases, the ratio of the critical distance decreases and eventually tends to be 0.8. The difference of fatigue limit ought to increase, but it becomes small when the radius is large. This is because the small stress gradient ahead of the notch tape leads to the insensitive of the prediction to the used critical distance in different methods. This is the summary of the first part. And the second content is about the stress ratio dependent of the material parameters. According to part 1, we can find that the fatigue limit and the fatigue crack growth threshold are the necessary material parameters for TCD and FFM. Besides, as we all know, these two parameters are stress ratio dependent. Many models have been proposed to solve this issue. Here, I'd like to introduce our method. In the high cycle fatigue, the dissipative energy can be divided into two parts, the elastic dissipation and the inelastic dissipation. The elastic dissipation refers to the internal fraction of the crystal, including the recoverable moment of dislocation, and the inelastic dissipation refers to the energy consumed by microcrack formation and microplastic deformation. This energy is responsible for the fatigue failure. When the applied stress range is lower than the fatigue limit, there is no inelastic dissipation. Accordingly, it is assumed that the fatigue limit corresponds to a critical elastic strain energy. If we use the strain energy density to represent the critical energy, it can be easily obtained by the stress strain curve. For the stress ratio bigger than 0, it can be expressed by the first equation, and for the stress ratio smaller than 0, it can be expressed by the second equation. Now, assume one test is carried out at the reference stress ratio RIF, and the corresponding fatigue limit is delta sigma E REF. Then the fatigue limit at other stress ratio can be obtained by the following equation. These two equations are for the reference stress ratio bigger than 0. Similarly, for RIF smaller than 0, the following equation can be obtained. Especially for RIF equals to minus 1, the following equation can be obtained. The right figure shows the fatigue limit prediction model based on RIF equals to minus 1. To validate our proposed model, we found 144 data points in the reference. The material includes steel, aluminum alloy, and non-ferrous alloy. It can be seen from figures A, B, and C that the proposed model agrees well with the experimental data. Figure D shows all the data together, and it can be seen that all the data uniformly distribute around the proposed model. Based on the fatigue limit model, we further derived the stress ratio correction model for fatigue crack growth threshold. The model is also verified with a large number of data in the reference. Then we compared our proposed model with some existing models. This slide shows the fatigue limit models. From the perspective of the needed parameters, our proposed model, as well as the SWT model, needs the least parameter. This means it is convenient to be used. Besides, we carried out error analysis and found the RMSE of our proposed model is the least among all the models. This means it has the highest accuracy. Similarly, we compared the fatigue crack growth threshold models, and our proposed model also has the least error among all the models. This is the summary of the second content. A new stress ratio correction model has been proposed for fatigue limit and fatigue crack growth threshold. It provides a way for getting the input material parameters of TCD and FFM. That's all of my report. Thank you for your attention.